Let's move swiftly to our next speaker. So Walterio Mayol Cuevas is a professor at the University of Bristol. He's also a principal research scientist at Amazon in Seattle. He has a nice connection to the previous talk. I wonder if he'll recognize this or dispute it. His PhD was actually on wearable visual robots. I think you've moved on to a broader spectrum of things than that, Walterio. Please, and you may wish to go into display mode with your presentation.
Yes, I think I am presenting already. Can you see my slides?
We see your slide, but you could be in slideshow.
Okay. One question I have, which maybe the interface changed here. I think there is a way to optimize for videos.
We investigated this earlier. Video looks okay to me, actually.
Okay. It's just that when I play the videos, I just wonder if they will work, but you will tell me. Thank you very much, Paul, for the nice introduction. And let me just go into indeed display mode. And indeed, today I'm going to talk about some recent work that my team and I have been working on that have to do with how to actually put decision and potentially learning in this new class of sensor processor devices. And everything that I'm going to talk about here is with my university hat, just for full disclosure. And this is this is a picture of part of the team that I've been working on, and you will recognize some names here. Yana, and I believe already presented in the workshop. Pyotr, of course, we are using his excellent architecture SCAMP. And just for the benefit of those that may be hearing this on their recording, let me just reframe the problem here, where essentially traditional division systems have been composed by a amalgamation of modules that have to work together, and they start with things like cameras that have been designed for recording images, not necessarily for visual processing. And these sensors often clog our data channels with lots of information. So there is a huge amount of bandwidth that is required to transmit video signals, as you will be aware. And usually what happens is that this enormous amount of data goes into a processor device. It can be a CPU more often, and because of the type of models that are being used for inference nowadays, we need external processors like graphic processing units, which again may not have necessarily originally been built for vision. They have moved significantly into the direction of handling things beyond graphics, but still we're talking about multiple components that are being used in order to process the significant amount of data that is coming from the conventional cameras. Eventually, you might make an inference, and this inference is sent to another processor that then conditions a signal that eventually leads to an actuator. So we're talking about vision for action. You have to go through a number of modules that send all this information, consume significant amounts of bandwidth, more energy consumption because of all the devices that are involved, and also system complexity, which complicates things. At the advantage of being able to just simply replace one of these modules if it is possible within your algorithm. But what we are really interested here in this workshop and the work that we've been looking at is how can you actually go from perception to action in a much more efficient way, so that we have the image sensing in a way that allows us to, at the point of image capture, extract high-level information, perhaps the direction of motion that we're moving, maybe the speed at which we are moving, maybe the identity of the objects or the location where we are. And we only output this high-level information, which is all you need for taking an action and potentially even directly connecting into some actuators. And what the advantages are, and as Yushin already mentioned, there are significant advantages for being able to do this type of close to the image point of capture processing. And they involve low energy consumption, low latency, you reduce system complexity, you can improve potentially privacy because you're only sending high-level signals. Of course, from high-level signals, you can still try to reconstruct and attack such a system in the encryption sense, but you're already not sending a lot of irrelevant information that otherwise you will be doing with a conventional vision system. However, I also want to add that there could be new opportunities here, apart from the ones that we're traditionally interested in. And that opportunity is new ways in which we can do the signal processing itself. And I will be hopefully talking a little bit about that today. But it's always good to take a step back and ask ourselves if some of these ideas are new. And I always make reference to this early work back from the 1950s when Levitt, Maturana, and McCulloch, three significant figures in the neurophysiology field, put a paper where they were talking about how the frog's eye processes information. And this is meant to be a frog that my 70-year-old drew for me. And what they discover in this paper is that the eye of the frog already does a significant amount of processing. Actually, a frog that is surrounded by food, but where nothing moves, it will starve to death. And this already tells you that the eye is not sending just wasteful amounts of information to the brain to act. It's actually deciding what relevant information needs to be sent. And we're not really talking about that the eye is able to detect things like black dots versus a contrasting background. What they discover is what they later called as bug detectors. So this is beyond just being able to detect black dots versus a nice clean background. These detectors behave to detect how these objects move in the visual field. So it's beyond just the visual appearance, it's how they are moving. So these are sophisticated inferences that are happening at the eye of the frog. And of course, the frog is interested in doing this so they can actually eat and trigger an action. The curious thing is that when Ledvin and his team talk about when they tried to publish this paper, they were essentially laughed at conferences because no one believed that the eye was doing more than just capturing images. And to some degree, we're still living in a world where we assume that our cameras are there to capture and record images and record detail. But the reality is that acting systems do not need to record wasteful information. They only need to record or actually process the information that is relevant for the tasks that they need to serve. So I think it's always interesting to talk about what is out there. However, I'm not arguing that whatever is out there in nature is the only interesting thing that that can happen. I believe there is a new opportunity here, something that, as far as I'm aware, does not happen in the natural world, and that is the ability of potentially learning and modifying the inference based on what is being perceived. So this can be very powerful because then we can have systems that can automatically learn and become efficient and process the information at the point of image capture without having to involve more sophisticated processing parts. And as a recap, You might have come across the SCAMP before in the workshop, but as a recap for those hearing this in the recording, essentially we're using a pixel processor array, which is the SCAMP developed by my colleague Kurt Dudek and his team at Manchester University. But essentially in SCAMP, what we have is that every light sensing unit has a processor. It has an ALU, it has multiple registers, it has flags, and it is able to connect, this processor is able to connect to its neighbors. So essentially you have a massively parallel architecture that allows you to do computation at the point of image capture. And then you can bring all these sort of things that we mentioned before about more energy efficiency, lower latency, and so on. The things that we've been able to do with this type of device involve several things that have to do from low-level signal processing to more high-level tasks like visual odometry, for example, or object detection. And let me see if this works well for you all. This is a very simple demonstration, but interesting. This is by Yan and Liu, who will represent in the workshop. And he put together this demonstration where what we have is a car that has a SCAMP device and is able to move around a place, recognizing from a potential universe of possible gates through which it can go through, which ones are the ones that it actually needs to go through. So as the vehicle is moving, is making decisions about which are the gates that you have to go through. And it's able to do this at relatively to the vehicle high speed. So let me just go to one of these other sessions. But by the way, are you able to see this video well over there?
It looks okay to me.
Thank you.
So
this is 3.8 meters per second on this small car, and is making decisions just like a slalom test that based on the pattern that is in there, it's making a decision to go left or right. So this is a basic demonstration of the type of things that you could be doing with this device. More advanced things, we have also done things like visual odometry. And because we're able to do processing at the point of image capture, we can, and actually important thing, this device is a general processing unit, because you can essentially upload different programs at any point and you can execute them pretty much with little lag in between. You can be running things like low-level image processing like HDR image capture, and then later you can be using the PPA to do inference on a CNN. Or as in this case, we are calculating HDR images and then able to compute visual odometry in relatively simple ways. The way in which our ICCV, we have a Laurie Boss is a lead author here, but we have an ICCV paper where we do very basic processing to calculate visual odometry. And essentially what we do is we calculate HDR images as they arrive, and then we perform distortions of motion. Essentially, we are applying a motion model, and based on the best matches, we're able to make an inference about how this camera has been moving. And then we can put it together in a way that allows us to have an understanding of how the visual odometry is working. So let me just go to this other part, but essentially here you see the camera moving around and the system estimating where it is. There will be a better visualization here where the camera is moving in a courtyard and you're making turns and the system is estimating how you're moving and when you're turning and so on, based on extremely simple vision algorithm here. And everything happening at, in this case, it was working around 1,000 frames per second. So We have also been able to connect this processing with other tasks, such as drone racing. So in this case, you might be familiar with drone racing, where essentially what you have is these gates in the environment. And in this case, we have a SCAMP system that is detecting these gates, is detecting these frames that are in there, and is able to decide that which one of these gates is the closest one, and therefore it goes through it. And then we have been able to also develop algorithms that implement CNNs on the SCAMP device. So essentially what you have here is a camera that is making inferences, and it's outputting only the identity of the objects that is able to see. So in this case, for example, this is using, again, a relatively simple data set, the MNIST data set, where we're able to detect in faster than usual real time what the camera is observing. And this is using a CNN in there. And the way in which we're able to do the CNN with a massive parallel computation that is in the PPA is, as an example, what we have in these recent papers. We have one paper in ECCV and another one in BMVC. They use slightly different ways in which these CNNs are implemented. One has more emphasis on speed, and enables us to process at tens of thousands of frames per second, depending on the classification challenge and task. But the way in which this works is that when we have an input image, we, in order to benefit from the parallel processing, we duplicate this image, which then allows us to multiply the different convolutional kernels. From which we can get an output that we can apply an activation function like ReLU, and then do other processing like Maxpooling, all in parallel, before we also use a fully connected layer also implemented within the PPA. So essentially, we can have a CNN that is in the device at the point of image capture, performing inference. And we can update the CNN with different tasks in real time. The way in which this works in slightly more detail is that we have the image. Here we have an example of a basic kernel that we are duplicating. And because we're duplicating all this, we can, in parallel, thanks to the way in which the SCAMP works, we can apply this kernel filter in order to be able to go to the next step of the network. And in order to increase the speed, we can also apply strides. So we can have strides of stride 4, for example, or other levels of stride, depending on if we can afford to do this mostly for the reasons of increasing speed of inference. And all the details of these are in the BMBC and ECCV papers that we have on this work. And then the same for the activation function. We can indeed perform the activation function in parallel thanks to this duplication, and eventually do Maxpooling, which after we do the Maxpooling, we're able to then apply the fully connected layer, where we can also store all the weights for the fully connected layer in our digital registers, which are then multiplied by the Maxpooling image to obtain a final result, which eventually leads to our classification. So this is a massively parallel application that we have on the SCAMP with the CNN. And this is a demonstration that Jan and Lou in the workshop already spoke about, but I want to emphasize again, because apart from the speed at which you can be doing inference with CNNs, with the SCAMP and these algorithms that we have, there is another important thing here to highlight, which is the very low latency that we can have. So in this case, even that the system is not implemented with the best possible technology for the SCAMP, and the actuator that we have here is fairly slow. Essentially, we can have from image capture, passing through inference to image class, and sending the signal out to the motor directly from the actual device. Nothing else is put in between in 120 microseconds, which of course is a very good number for fast reaction. We have also worked on other data sets, for example, classifying plankton or MNIST numbers, and depending on the classification challenge and task, we can achieve different frame rates. The other thing I want to talk about is we have spoken about inference, but most of the inference, essentially all the inference that I spoke about, happens on the SCAMP. However, the training and the learning happens offline. So we train offline, and then we port into the SCAMP the model that is then executed. But what if you actually want to learn as you're processing signals and then do inference at the same time? So this is not full SLAM, I will say, because we actually have distinctive steps in terms of mapping and localization, but this is perhaps one of the first, if not the first, on-sensor mapping and localization work. And it has been presented here in ICRA 2021, and is a work of Hector Castillo Elizalde. And essentially what we have is a topological navigation framework where we have nodes, which are pictorial nodes. So these are images that have been represented with small images or with descriptors, and then we use this information in order to know where you are. And we have in the paper explored two different ways to represent this information. One is to use descriptors for the images that we're observing, and the other one is using small images like 8x8 pixel images, which other systems have been shown to be able to do fairly good and robust detection, even with small images. So essentially what we have is a mapping procedure where we capture all these nodes, we put them into the SCAMP registers, and then here's an example. As the camera is moving, we have actually tested two methods for mapping here. One is based on the difference between the previous image and the incoming image. If we see enough difference, then we actually create a new pictorial node into the system, which is probably hard to see, but it's growing here. So these are the nodes that the system is capturing. That's one way. The other way is just every temporal interval, we add a new node. And then we test these two different approaches for the image representation. But what you essentially end having is something that allows you to do mapping and localization in a way that is reminiscent of a particle filter, because we have nodes, we have weights, we improve the likelihood, and we have a motion model that allows us to know where we are. And in the interest of time, I think I am going to play the video, which is here, and that in a minute summarizes what we're doing. Let me know if you can see and hear well.
In this work, we present a method of visual localization performed directly on the focal plane of the pixel processor array sensor. PPA sensor incorporates processing and memory into each pixel element, allowing visual data to be stored and processed on sensor.
So it's very quiet, Walterio.
Our approach involves first capturing a visual database onto the focal plane from a sequence of select images.
Is that better?
Select image is encoded as a node in this database.
I think we could go a lot louder.
The PPA is used to directly compare each new image with every node in the database simultaneously. This comparison is used to update the weightings for each node based on the visual similarity between it and the new image. When combined with a motion model that transfers weights between nodes based on camera motion, This approach allows localization to be performed over a sequence of images, effectively by determining the best matching sequence in the database. We test our approach on a number of video datasets. Here we see the Nordland train dataset with a database of branded descriptors generated at a different time of year than the video sequence used for testing. Despite the visual differences between seasons, our method is able to localize along many parts of the dataset. We also tested our approach on both urban and simulated video sequence datasets, testing both databases constructed of binary descriptors and low-resolution images. It has demonstrated results comparable to similar methods, while conducting all significant computation on the focal plane of the PPA sensor, rather than using external hardware for this processing.
And full details on the ICRA paper for this work. Okay. So essentially, with this, I will close my presentation, and essentially, it's a reaffirmation that the notion that we have to split the sensor decision making and action is overly simplistic and highly inefficient. So as we want to move into systems that are better for IoT reasons or for robotics, then clearly we will benefit from different ways in which we want to create these visual pipelines. And so redefining the way in which we process visual signals is very important, and a significant component of that is the type of hardware and the frameworks that we're wanting to develop for this. And just as an open question, one of the things that I believe is coming from the point of view of this in this space is trying to understand where can we do what processing, and trying to understand what are the best places in which we can and we should be doing what visual processing. Okay, with this I finish, and I don't know if we will have time for questions, but if not, as Paul mentioned, we can also talk about that in the discussion panel. Thank you.
Thank you very much, and let me lead a round of virtual applause. Let's take a moment for a couple of questions if we can. The YouTube people are a little bit lagged. You can still type a question in the chat there. I'd very much like that. But meanwhile, perhaps there's somebody on the Zoom call who has a question. While you think of that, I'd like to ask you, Walterio, this question, and this is a question you asked me, so it's a little bit unfair. You touched upon it a moment ago. What tool support do you imagine might help us map the computational pipeline onto a system with multiple layers of processing, from in the focal plane to near the sensor to perhaps in a visual processing unit and so on? What do you imagine that programming model should look like?
I think this is indeed a very important question, Paul, that I don't have the answer. I mean, at a high level, you can imagine that you can formulate everything as an optimization problem. So it should be possible to formulate an optimizer. So like network architecture search is doing, right? So where you will be able to formulate a problem as an optimizer, where you have your constraints, maybe you have things that you're able to measure relatively easy, like the energy consumption, if you have a decent way to simulate that, or the lag that you are going to achieve, or the bandwidth that is going to be crossing the different modules that you have. So you can formulate some of these things as an optimization process, and I believe that is like the most obvious thing to start with. However, there will be other tasks, like we have touched on. Are the systems better for privacy? How do you formulate things that are more subjective like that into a mix that you likely, especially when we talk about vision processing, likely will need to be considered? So this is what I think still needs quite a lot of research. But in very general terms, I can imagine something close to an optimizer, maybe close to natural architecture search.
Thank you. Is there another question quickly? In that case, let me thank our speaker again.